is Mark Smitty Smith. He is, I'm going to say a bunch of nice things about him to embarrass him. Mark, he's a really good dude. He has been very generous with his time and knowledge with me, and patient with my smart-ass remarks. He is a super duper smart nerd. He is a maker and a tinkerer. He's by trade an IT geek. He is in the SLO area, San Luis Obispo area. So he's local-ish, but not exactly local. He has been in the area before. You guys may have met him at the Micro Expo last year. Mark was there with the eggnogs and a few other things. He is the proprietor. He started Halibut Electronics. Some of the products that he's got on there are eggnogs, contesting console, the OHIS, which is one of his passion projects, the Hali key, which I actually have in my backpack over here, and then the CMCC, the common mode current, there's the Hali key, and the common mode current test rigs, which are frankly my personal favorite. He knows that, so when I said, hey Mark, would you talk to our club? He said, well, I know you like those things, so why don't I do a common mode talk? I use, it's something that I use, so I brought my regular one and my digital one. After his talk, I brought a nanoVNA, so I can actually show how we would, show a live measurement of a choke, because I also brought a Type 31 Torre. So again, thank you very much, Mark. Take her away.
Thank you. Sorry, I'm realizing that I have a common mode current choke test rig right here that I had hooked up to the VNA. I was taking some measurements with it earlier today to update some slides on the presentation today. So I just wanted to disconnect it from the VNA to bring it up for the thing. Okay, let's go straight into it. Can you confirm that you can see my slides and my face in the upper right-hand corner?
We can.
Okay, very good. Well, thank you very much for having me. Like Matt said, my name is Mark Smith, N6MTS. I am known around the internet as Smitty Halibut in various different places. I am the president and CEO of Halibut Electronics. That just sounds way too pretentious, though, so I usually just go by head cheese. The webpage is there, electronics.halibut.com, but we'll have links to that at the end. So, who am I? Well, again, I said my name, my call sign. I used to be known as KR6ZY for about 20 years. Before that, I was AD6SE. Before that was KQ6ZQ. That was probably the call sign I was most well motivated to get rid of. And I originated as KD6JTS. So I've had a bunch of different call signs. But N6MTS, I am officially in the initials as call sign club, so I don't see that changing anytime soon. My primary hangouts on the internet are YouTube and Discord, and in both places I am Smitty Halibut. I am also on Mastodon, although not nearly as often as I used to be. I am at Smitty at halibut.com there. And I am a sometimes host of the Ham Radio Workbench podcast. In fact, I had to duck out of a recording tonight to come here. So that's who I am. Let me give a quick disclaimer on tonight's presentation. I am going to be playing it a bit fast and loose with numbers. Like, I promise you there won't be any math in this presentation. It's going to be kind of conceptual and just like high level. I want you to kind of get a feel, an intuitive feel. That's the word I was looking for. An intuitive feel for what's going on with common mode currents. Why they're bad and why we want to get rid of them and how to get rid of them. And then at the latter half of the show, we'll be looking at a bunch of different measurements of various different common mode current chokes and comparing different designs. If you want the actual detailed engineering stuff of this, these are two resources, and again, we'll have those links on the last slide, so you don't have to take a screenshot now or whatever. These are two very good resources that talk about common mode current and chokes and whatever else. There is a third that I was not able to get into the slides, and I'm totally blanking on the guy's call sign. Anyway, there's another resource that I want to add here, and I'll send a link to it to Matt after we're done. So that's who you talk to and what you read if you want the actual math nitty-gritty engineering stuff. This presentation is going to be kind of high level, intuitive, giving you a feel for how it all works. All right, well, if I'm not doing any new engineering, then what is it that I'm bringing? And what I'm bringing, I need to update that graph. What I'm bringing is measurements. I am not just talking about theory. So I'll get into why common mode currents are a little difficult in a little bit, but they are not something that our normal test equipment can easily measure. We have to do things to be able to get our, our VNA, the nanoVNA, which is one of the most common tools around these days because they can do so much and they cost so little. They're amazingly powerful. They can't measure a common mode current choke directly. You have to do stuff to it before it can actually measure it. Consequently, very few people actually measure their chokes. And so there's a lot of common wisdom, a lot of accepted best practices around for how to build a choke. And not all of that wisdom is very wise. Some of it is, but not all of it is. And so I want to be able to quantify that. And that's what we're going to be doing here. All right, so let's start at the top. What is common mode current? Well, common mode current is in opposition to differential modes current, right? So we've got these two different types, common mode and differential mode. Differential mode means you've got a transmission line. A transmission line is two wires, right? And you've got some amount of current going down that direction on one of the wires and an equal amount of current going the opposite direction on the other wire. When those currents are exactly balanced, that is differential mode current. All right? This is not the same thing as balanced versus unbalanced in voltages. That's a voltage thing. Here we're talking about currents, and that's why we use the term differential mode and common mode as opposed to balanced and unbalanced. But it's kind of the same thing. Differential mode current is where you've got the same amount of current going in different directions, opposite directions. Common mode is where you have current flowing only one direction on that transmission line, right? It's either flowing on one of the two wires or both of the wires, or turns out it doesn't actually make a difference. It's just that whatever current is flowing on that transmission line that is not balanced with another current going the opposite direction is considered common mode. All right, so let's take the example of where I've got 3 amps flowing that way on one wire and 2 amps flowing that way on the other wire in my transmission line. Well, there's 2 amps that are balanced, right? So those 2 amps are differential mode, but that difference, that 1 amp that is left over is common mode, right? So you can have common mode and differential mode on the same transmission line at the same time. And that's just where you have, you just sum them together. So if I've got 2 amps of differential mode and then 1 amp of common mode, then I've got 3 amps on this wire and 2 amps on this wire. So does that make sense on what the difference is between common mode and differential mode?
Yep.
All right. So the example that I just gave you was for parallel wire transmission lines. You got 2 conductors, traveling parallel to each other. Coax isn't different, but it has a few things that are a little bit weird about it. The short version is that differential mode always travels on the inside of the coaxial cable. Necessarily. So because physics, and I won't go into the details here, but if you want to look it up. It's a combination of the skin effect and proximity effect. Differential mode currents, balanced currents, always flow on the inside of your coax. So it'll flow on the center conductor and then the inside of the shield on your coax. There is no current flowing on the outside of your shield if your currents are perfectly balanced or perfectly differential. Okay, that's the whole point of a shielded cable, is that we want to keep all of our currents on the inside of that cable so that it doesn't act as an antenna. If you have any common mode current, that common mode current necessarily travels on the outside of the shield. You cannot force a common mode current to flow on the inside of a piece of coax. And there's a neat thought experiment here. Okay, well, what if I leave the shield completely disconnected and I just run an RF current? By the way, all of this applies to RF. DC is different. This is RF currents. I'm going to send a common mode RF current. I'm going to connect it to the center pin, and I'm going to, put a load on the other side of it, but I'm going to leave the shield completely disconnected. Obviously, that'll have a common mode current flowing on the center pin, and the shield won't have any current flowing on it, right? Because it's completely disconnected. No, it's actually weird that you've got some amount of current flowing that way on the center pin. It will actually induce a same amount of current flowing the opposite direction on the inside of the shield to balance it, to make that differential mode, right? And then once that current hits the end of the shield, it goes around flips around the end and starts flowing that way on the outside of the shield. And so these two 1 amps, you got 1 amp going that way on the inside and 1 amp going that way on the outside. They sum to zero, so you're not creating current out of nowhere. But that 1 amp or whatever that current is that you put on the center pin magically shows up on the outside of the coax. It even though the shield is completely disconnected. Kind of RF magic. This is a bit of a tangent, but it's RF magic. Really, truly, the inside of a coax is only ever differential mode, and the outside of a coax is only ever common mode. Okay, so let's move on. What causes common mode currents? Well, the short answer of that is that there are a lot of different causes, but there are two primary causes that we care about as ham radio operators. So we've got here, can you see my mouse? It's pretty small, unfortunately.
Yes, we can.
Okay, so over here we've got an antenna, but it's a little wonky. It's not perfectly symmetric. No antenna is perfectly symmetric. It's just the realities of where you put it up, right? Even if you have a dipole, it goes up near your house or near a tree, or the pole, it's a little bit wonky or whatever. There's no such thing as a perfectly balanced or perfectly symmetric antenna. And so some antennas are worse than others, but your antenna is going to be causing a little bit of reflected power. Now, this is different than the reflected power that shows up as SWR. I have to go into a little bit more engineering on this, and I promised you there wasn't going to be, so we won't. This is different than the stuff that shows up in your SWR meter. Your SWR meter is measuring reflected differential mode. This is caused by asymmetry between the two different conductors of your transmission line, and that will cause common mode to come back down on the outside of your coax of your transmission line. If you've ever heard the term, I've got a hot mic, like where your lips touch your microphone and you get a little bit of a tingle, or whenever you key up your CW keyer, all of a sudden your lights flicker, or your computer disconnects from the network. Any of those kinds of gremlins that you have anywhere in your shack or your house that happen when you transmit, that is common mode. That is RF either being reflected by your antenna on the outside of the shield, or just being conducted directly into your to the outside of your coax or your transmission line, because it's a wire and it looks like an antenna. So that is kind of the transmit high power common mode that we want to eliminate. The other kind of common mode that we want to eliminate is that the outside of this coax looks like a wire. and that wire goes straight into the receiver. And that receiver has a ground connection. And if that were a perfect ground and there was no impedance anywhere between that RF connector coming into your transceiver and that ground connection, either through your power supply or through an earth ground or whatever you have, if that was perfectly 0 ohms impedance, then any currents coming in on that outside of that coax, sorry, I forgot to say where these currents are coming from. Let's say your feed line runs right near some LEDs, some LED lights, or I don't know why, but washing machines seem to get a lot of the blame on this. But if you've got some source of noise, RF noise being generated anywhere near you, even if it's a very low power output, but your coax runs close to it, or if it's a high power output, it doesn't have to run very close. Anyway, any RF noise that you don't want in your receiver will come in on the shield of your transmission line. And if the path between the input to your transceiver and to the ground is anything other than a perfect ground, that common mode is going to flow through that impedance from your transmission line to ground, and that impedance will cause a voltage, and that voltage will show up in your receiver. It's not a lot of voltage, but remember, our receivers are dealing with minus 120 some odd decibels, right? Like, we are talking microvolts. Is it nanovolts? No, I think it's microvolts. We're talking very tiny voltages that your receiver is detecting and sensing. So any currents that are flowing through your ground system there will show up in your receiver, and you get noise, right? So this is the mechanism for, I've got a bunch of common mode on the outside of my shield, and it's making noise in my receiver, okay? So those are the two main things of common mode that we want to eliminate. One is the transmit imbalance from your antenna, and the other one is the noise coming into our transceiver. All right, great. So how do we deploy, or how do we fix this? Well, we want to take my word for it for now. We've got a magic device called a choke that will pass differential mode and block common mode. Right? We want to design a magic device that does that. And if we have that magic device and we put one at the feed point of the antenna, what that'll do is that'll block any of the common mode coming down from the antenna, and it will block it from flowing on our transmission line. And it forces all of that current to stay up in the antenna. In more technical terms, it increases the impedance of that feed line so that the lower impedance of the antenna takes way more of that current than the feed line does. So what we want to do is we want to increase the impedance to common mode without affecting the impedance of the differential mode. All right, so if we put one at the feed point of our antenna, that blocks any of the currents coming from the imbalance of our antenna. If we put a second one at the input to our transceiver, that will block any of the RF that has been picked up by our transmission line, the outside of our transmission line, any of that common mode, it'll block that from going into your transceiver. It makes a super high impedance here, which will drop the vast majority of the voltage, and so that the small but non-zero impedance here between there and the ground doesn't get a whole lot of voltage out of it. So that's where we want to put our chokes. Any more chokes in there, it's not going to cause any problems, but those are the two primary places we want to put chokes, at the feed point of our antenna and the feed point of our receiver. All right. So I waved my hands and said we've got a magic device called a common mode current choke, and it blocks common mode but allows differential mode to pass. How does it do that? If you remember your electronics theory from your test, from your ham test, your license test, we have three main types of components that we deal with in electronics: a resistor, a capacitor, and an inductor. Yes, there are a lot more, but those are kind of the three fundamentals. What we're talking about here are inductors. An inductor will pass low frequencies but block high frequencies. And then the value of the inductor and the value of the load and everything else determines where that cutoff is between low frequencies and high frequencies. But in short, what we want to do is we want to make a large inductor so that it will block the RF, but we only want that inductor to be effective at common mode. So let's look at what we do here. We've got a choke, or excuse me, a ferrite that we wind our transmission line over the ferrite, and we turn the transmission line into an inductor. Okay? But if I take both wires of that transmission line and wind them next to each other into an inductor, all the differential mode currents, the current flowing this way will create a magnetic field. We've got the right-hand rule. If you've got current flowing that way, it'll create a magnetic field with where your fingers go this way. But if you've got a current going the other direction, it will create an opposite magnetic field. So currents going in opposite direction create opposite magnetic fields. Those magnetic fields cancel each other out. And you need a magnetic field for an inductor to do anything. If there's no magnetic field, the inductor doesn't see it. It doesn't exist as far as the inductor is concerned. So differential mode with currents flowing in opposite directions will cancel their magnetic fields, and the inductor doesn't see it, and it passes right on through that inductor. But common mode only has current flowing in one direction, and that one direction doesn't have anything to cancel it out. So it does create a magnetic field, and that magnetic field interacts with that inductor, and if we make that inductor large enough, then it will block those common mode currents, those RF currents at common mode. Does that make sense? Like, the whole magic here is differential modes, currents going in opposite direction. That's the current we want. We like that current. It creates no magnetic field because the magnetic fields cancel each other out. So it goes right through the inductor. But the common mode is the stuff we don't want. It does establish a magnetic field in the inductor, and the inductor blocks the high frequencies of that. Are there any questions on that part before we move on?
I do have a question. Hold on. Yeah, would the magnetic field caused by the common mode have an effect on the differential mode?
Have an effect on the differential mode? Is that what you asked?
Yeah, so the
Yeah.
common mode is creating this magnetic field. Would that magnetic field from the common mode then affect any differential mode current going through this?
No, it would not. Because the technically speaking, they're not different fields. They're all the same magnetic field. It's just that the the differential modes, they cancel it out. So, again, let's go back to that example I had before where I've got 3 amps going that way and 2 amps going that way. I've got 2 amps worth of magnetic field. I'm going to wave my hands at that. 2 amps worth of magnetic field going, wrapping around the wire this way, and 3 amps of magnetic field wrapping around this way. 2 of those amps disappear, and that one remaining amp is the one that sets up the magnetic field. So, no, the common mode does not affect the differential mode in the magnetic fields at all. Okay, cool. All right. So now we know what common mode current is. We know where it comes from. We know where we want to put a device to get rid of it, and we know the theory of that device. Let's measure them. All right. So we're going to use a VNA. The real popular ones nowadays are called the nanoVNA, but everything I'm going to say here is true of any VNA, whether you paid $50 for it or $50,000 for it. A VNA is a 2-port device, right? Okay, I assume you all are familiar with an antenna analyzer. If you're familiar with what an antenna analyzer does, it generates a signal going out an RF port. You send it up to your antenna. The antenna reflects some of it back and sends it back down to the antenna analyzer. Excuse me. And the antenna analyzer is able to measure the forward power and the reflected power and do a bunch of math and come up with an SWR. And also resonance plots and a few other things, okay? If you're familiar with that, a VNA is just, or excuse me, an antenna analyzer is a one-port VNA, all right? So the VNA port 1 is your antenna analyzer. It generates a signal, and it sends that out toward your load. In the case of an antenna analyzer, that is the antenna. And that load will reflect some amount of that energy back toward the VNA. And that comes back in on the same port, okay? And then the device, VNA in this case, or the antenna analyzer, it knows what it generated, and it knows what it received, both the amplitude and phase of both of them. And it's able to measure those, does a bunch of math, hand-wavy math, and can give you a lot of really useful information on it. Things like SWR and complex impedance and all kinds of fun things. The only thing that a VNA does over an antenna analyzer is it adds a second port. So it can measure the signal as it comes through the device that you're measuring, not just the stuff that was reflected back. All right, so we have the second port over here, and we're going to take some amount of this energy, it goes through the load, is affected by the load, and then comes in on port 2, right? So now we know what we generated on port 1, we know what we measured on port 2, we can do a bunch of math and come up with some very useful information here. And in this particular case, we're going to be measuring what's called S21 log mag. So you may have seen things like S21 or S11. What that means is it is a measurement taken on port 2 of what was generated on port 1. So that would be an S21 measurement. It is measured on port 2 of what was generated on port 1. So we are going to be measuring S21s, going out on port 1 and in on port 2. Your antenna analyzer can only make S11 measurements. Goes out on port 1 and comes right back in on port 1, the reflected stuff. All right, so that's the difference between the S21 and the S11. Okay, so we have a bit of a conundrum. The VNAs that we want to use to measure this, they are generating their signals as differential mode, right? Everything we want is differential mode. We want our radios working in differential mode. We want our receivers working in differential mode. We want everything doing differential mode. So all of our test equipment is in differential mode. In terms of a coax, it means that all the current is flowing on the inside of the coax. But we need to be able to measure the outside of the coax. And a VNA can't do that, or at least not without some trickery. So what I'm going to do is I'm going to build a test rig. And the schematic is super simple. It looks exactly like this. We've got some SMA ports here that connect to the VNA. And the center pin of that signal coming from the VNA is going to get connected to the shield of another connector that we're going to connect our device under test to, our choke that we're trying to measure. And it goes out, goes through the choke, and then comes in on the shield of another port, and it gets put back on the center pin. Okay? So we're taking the signal from the center pin, putting it on the shield, running it through the device we're measuring, and then putting it back on the center pin so that it can be measured. That's actually not the special part. The special part is that we are running the return currents directly back between the SMA ports. Because remember, we want this to be common mode, not differential mode. So if I ran both the center pin and the shield, like if I just reversed them so that the center pin connects to the shield and the shield connects to the center pin, that would still be differential mode. It would still all be flowing on the inside of the coax. That would not do what we want to do. We actually need to take the coax coming from our VNA and split it so that just the center pin goes through the device we're measuring and the shields connect directly to each other. We need that current to not flow through we need that return current, the shield currents, to not flow through the device we're measuring. So the critical parts of this design are the fact that the shields of the VNA ports are connected directly to each other, so all the return currents are going through that, not through the device we're measuring. And then we're connecting the center pin to the shield of the device that we're measuring. So this was my first design of a common mode current choke test rig. And you can see the SMAs here on the side are the ones that connect to the VNA. And it's kind of hard, it's better to see on this one over here. You can see the center pin connects over here to the shield of these SO239s, and then I also put in some SMAs and BNCs on the other side, but it's only connected to the shield, not to the center pins. You see the center pins on all of these connectors are disconnected. They have nothing connected to them because we're only going to be running common mode through the shield. And then here's the critical part where I'm connecting the shield of this port on the VNA directly to the shield of this port on the VNA. So this is what causes our currents, the return current, not to flow through the device we're measuring, and that's what makes it a common mode tester. I built a second one. The first one was kind of running into some limitations. I didn't have all the ports I needed for all the chokes that I wanted to measure, and I wanted to put a switch in there that would allow me to go back and forth between measuring common mode and differential mode. When you measure differential mode on these things, all you're doing is measuring the insertion loss, and that ended up not being nearly as useful as I thought it was going to be, so I took it off on later versions. But this was an attempt to make a bigger, more sturdy, better option. And these are the two that I used to take the measurements that I originally made for this presentation that I gave on the QSO Today Ham Expo back in 2021. At the time, I was still working for my former employer, and I did not get, or I wasn't in business for myself. And the most common question I got from people after I gave this presentation was, where do I get that test rig? And I'm like, I don't sell things. You can just build it yourself. The designs, it's not that hard, but whatever. And then I left my former employer and started up Halibut Electronics. And so I guess now I am in the business of selling kits. So this was actually the first product I ever made, which was a board version of that common mode current choke test rig that I made previously. If you want to get it, it's electronics.halibut.com/CMCCTR, common mode current choke test rig. It's also linked to from just the landing page. But this is it fully assembled. This is it unassembled. It comes as a kit. These are all the parts you have to solder in. And then I also have a version for digital cables because not all common mode is on RF cables. Sometimes you get common mode on your Ethernet cables or your USB cables or your sound cables or your power cables. So the digital version of this kit will let you measure chokes that you build on any of those cables. All right, enough of the sales pitch. VNAs. You must calibrate your VNA before you take any measurements that you expect to trust. This is true of any measurements you take with a VNA, but it's especially true here because the common mode current choke test rig has a bunch of stuff all over it. It's got some parasitic inductances and capacitances and weird warts and everything like that. And you must calibrate the VNA to give it a chance to subtract all of that from your measurements. So it is critically important that you calibrate your VNA. Now, the good news is the kits that I sell have the open short load isolation and through. They have all of the calibration standards on the board itself. So you don't need to use your little SMA caps. In fact, you can't on the current version. All of the calibration is done on the board itself. There's some switches on the back that you flip to put in the right state to get it to calibrate the correct way. And that puts the measurement plane right at that circuit board. Everything on the input side of that circuit board, on the VNA side, is calibrated out and does not show up in your measurements. Everything on the output side by the device under test, everything over there is in your measurement. So it clearly defines where your measurement plane is. All right, so let's start taking some... Oh, no, sorry. First off, the next thing you do after you calibrate it is validate your calibration. So when you have a totally open, this is the isolation mode of your calibration, you should be reading nothing. It should be down here at -80 or less. The common mode current choke test rig is kind of big, and there's like capacitances between these parts, and so it's not perfect. But we get up to about minus 45 dB of crosstalk between the two channels when the test rig is connected. That's okay because we are interested in reading, around 20, 25, maybe 30 dB. So we're still above the noise floor of our VNAs. But once you short your VNA, when you just connect a jumper wire between the input and the output side on the test rig, you want that to be as close to 0 as possible. And so this was a measurement I took. You can see the yellow line is up here at 0. So there is no loss. You are measuring no attenuation of the common mode when you just have a cable going from one port to the other, from the input to the output. And that's what your cable is before you put a choke on it. It has 0 dB of attenuation of the common mode. Let's talk a little bit about what we're measuring here. We are going to be measuring the S21 log mag, is what it's called on the nanoVNA. What the heck does that mean? S21, we talked a little bit about that earlier. S21 means we are making a through measurement, not a reflection measurement. So we're measuring on port 2 what was generated on port 1, okay? Log mag. Log meaning logarithmic. Basically, we're measuring in decibels, and mag meaning magnitude, as in how many decibels up or down is the signal we're measuring on port 2 relative to what was generated on port 1. So I want to know how much attenuation we're going to be looking for negative dB of the signal coming into port 2 that came out of port 1. So looking for S21 log mag in negative dB numbers. Okay, great. What's good? What should we be looking for in terms of a choke? What is good enough? Well, the less S21 gain, as in the more negative the number, the better. And smarter people than me say that we want at least 1,000 ohms worth of resistive impedance. When you put that in series with your 50 ohm, blah, 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 blah. I was told there would be no math in this presentation, so we're just going to summarize all of that and say you want an S21 gain or S21 log mag of at least minus 25 dB. If it's a bigger negative number, like minus 30 or minus 35, that's good. If it's a smaller negative number, that's still good. It's just not as good as it could be. Like the target we're looking for is minus 25 dB. If you've got minus 25 dB, don't bother working any harder to make your thing any better. It's good enough. If you've got less than 25 dB, it's still worth deploying. There is never a point at which deploying a choke will hurt your system, except for the insertion loss of adding the new connector and the additional coax and all that. Assuming that your choke is not broken, adding more choking to your system will never hurt. So if your choke is only 5 or 10 dB, that's not that big of a deal. Go ahead and deploy it. You could do better, but don't not deploy it because it's not high enough. But the attenuation is not the only thing we want to look at. So I'm going to sneak ahead and show you one of the things that we're going to measure a little bit later. This is a Gordian knot, 7 turns of a Gordian knot. And look at that response curve. It starts up at 0. We basically have 0 dB of attenuation, maybe like 2 dB of attenuation at 3 megahertz, right? Now, at its peak, it's great. It's minus 40 dB. But at the minus 25 frequency range only covers one band. It only covers 15 meters, right? And it outside of 15 meters, it starts getting worse and worse and worse, and a lot worse. This is a very resonant graph where you have a very deep valley, but outside of that valley, it's really crummy, right? And that resonance comes from having too much capacitance with your inductance, right? So you make an inductor by wrapping a wire in a coil. This is a wire in a coil, but they're all tied up next to each other. And so now I've got a piece of coax here that's coming into the choke and a piece of coax that's right next to it going out of the choke. And those two things next to each other make a capacitor, and capacitors pass high frequency. So the capacitance allows the signal to go right on through the choke. So you don't want to have too much mutual capacitance. When you have a capacitor and an inductor in parallel, it makes a resonant circuit, and that's what this graph looks like. And we don't like resonant circuits. We want this to be purely inductive, not capacitive. So this is an example of just looking at the dB of attenuation is not everything you want to look at. So the other thing what we want to use as a definition of good enough is that it's minus 25 dB or better across as much of the band that we care about as possible. Okay, so those are the two things we're looking for. We want it wide, and we want it at least 25 dB down. All right, so I'm not going to make you wait until the very end to find what I have measured as the best common mode current chokes. If you can wrap your coax around a toroid 10, 12, 13 times, whatever you can get around that toroid without causing problems. If you can wrap your coax around that toroid like this, you will have one of the best chokes that you can for the money. You're only paying for one toroid worth of ferrite and then some coax. And you wrap it around, and you know, here's the minus 25 dB point, and this graph goes all the way down to 1 megahertz, right? So this is minus 25 dB or better. Like here's the 30 dB line, it gets down almost to 40. So it's between 30 and 40 for the vast majority of the HF spectrum. Sorry, this is 1 megahertz to 31 megahertz that we're measuring here. And sorry, I'm looking off to the side because that's where my screen is. I guess I can see it up here too. So, you know, this is a really good choke. It is wide, and it is mostly below 25 dB, except at the very low end. All right. But you can't always wrap coax around a toroid like that. Maybe you've got LMR 400. LMR 400 is not very bendy. It doesn't like wrapping around toroids unless you've got ginormous toroids. So the other option that I have found that works really well is to make a 3-turn loop. Now, you might look at that and say, well, that's only 2 pieces of coax there. That is true, but a turn is a time that the coax passes through the ferrite. So this is a 3-turn loop because the coax comes in, goes around once, comes in again a second time, goes around a second time, and then goes in a third time, and then just comes straight out there. So this is a 3-turn loop. So make a 3-turn loop. Don't do any more than 3 turns because then you start getting too much capacitance like I was talking about earlier. But 3 turns through that ferrite, the inductance of an inductor goes up with the square of the number of turns. So 3 turns is 9 times what it would be if you just clamped the ferrite on it. 2 turns would be 4 times better than what it would be if you just clamped a ferrite on it. So we want to wrap it around as many times as we can to get that square law advantage, but any more than about 3 and we start getting pretty resonant. But only one of these doesn't provide a whole lot of attenuation. But the good news is we can add more in series. And so if you add a second one here, just a little bit farther down the coax, and do another 3 turns with another clamp-on ferrite, those inductances add, and the capacitances divide. An inductor in series will add, those values will add, so you have more inductance. But capacitors in series divide, like resistors in parallel. It's the exact same math. A capacitor in series will divide. So when you put the capacitance of these 2 coils in series, they get less. So you have more inductance and less capacitance. It actually makes it less resonant. You end up with a much better, flatter graph out of it. So this graph, or this choke right here, is pretty darn effective. It's not quite as effective as the other one, but it's still at minus 25 dB, still around, maybe around 80 meters. And then it just, it stays below 25 for the entire rest of the band. And this is a choke that you can make with coax that's already in place. You don't need to feed the connector through because as long as you have enough slack, you can just twist a few turns and then put a snap-on, clamp-on ferrite on it. I was using one earlier today. Anyway, oh, here it is. So I have these very large ferrites. They're clamp-on ferrites. They have an internal diameter of 1 inch. The inside diameter of this thing is 1 inch. And so you can fit 3 passes of LMR 400 through this thing. So you can make a 3-turn loop on LMR 400, clamp one of these things on it, and then do 2 of those in series, and you will have an amazing choke. Okay, so let's do some measurements. So we were talking earlier about Gordian knots and why they suck. This is, okay, so I forgot to talk about this. Whenever you see a black graph like this one, this was taken several years ago. I took this when I first put the slide deck together, and then the white graphs are ones that I just took earlier today. It's different hardware. I don't have the same chokes around. I'm using a different test rig, so the graphs are not going to line up perfectly, but they're still very similar. Point being that this graph of a 7-turn Gordian knot looks different than the previous graph, but the important part is still there, that it has this super deep resonance point that makes it not very good outside of that resonance point. All right, well, at what point does that start happening? So I'm going to use this blue line. This blue line is our reference. Everywhere you see this blue line, that blue line is the same as this line here. All right, so I'm going to use this 13 turns through an FT 140-43 as our reference line. This is what I'm considering a really good choke. All right, so this is that blue line here. You can see how this Gordian knot is much worse than the blue line through most of the band. So let's look at how many turns in your Gordian knot results in what kind of graphs. So here's that blue line, that's our reference. If you just have 2 turns, which is a single loop, no ferrites, no nothing, we just have a single loop, you get about 9 dB up here at 10 meters. You know, it's really not very good. You add a third turn, a second loop, and it starts getting better. It's still pretty crummy down here in the low end of the band, but it starts getting better up in the high end of the band. But as soon as we add another turn and we get up to 4 turns, here's that resonance point we were talking about, right? This right here is why I say don't do more than 3 turns on this design. Don't do more. Oh, dang it. I've been pointing at my local screen, not at the one that you can see. I'm sorry. This design right here, don't do more than 3 turns through each of these clamp-on ferrites. And this is why I say that. Because once you get up to 4 turns, you start seeing this resonance here. And that's not good. We don't want that resonance. And then if you go up to 5 turns, the resonance just gets lower. And yeah, badness happens. So 3 turns seems to be our sweet spot for making simple loops. What happens when we clamp a ferrite onto it? So here is 2 turns with no ferrite. This is the same graph that was on the previous slide. And then here's 2 turns with a mix 31, in fact, this exact one, clamped onto that very same 2-turn loop that we made. You can see how it drops from, this was between 0 and 10. Now it's better than 10, 15, down to 20, and up at 20, almost 25 up at the high end. Just by adding that one clamp on ferrite, we improved this choke dramatically. Okay? Well, what happens when we do the same thing with the 3-turn? Right? So here's the 3-turn. It got a little bit better without the choke, but it's better still with the choke. Right? So this graph right here is 2 turns with the I'm sorry, I've been saying choke, the ferrite on it. And when you add another turn with the ferrite, it just brings this down a little bit lower, closer to our reference here. So this is 1 3-turn with a clamp-on ferrite on it. And you can see that we've got that same kind of shape of the other graph. It's just not quite as much attenuation as we would like. So, then we do the same thing with 4 turns with ferrites, and yeah, you can see that things, we still have resonance to worry about even when we clamp a ferrite onto the thing. And so it's really crummy up here, even though in theory we should be having more inductance. And then same thing with 5 turns. So we definitely don't care about 4 and 5 turns. In fact, I don't bother measuring them going forward. Okay, so if we have 3 turns of RG8X with 1 mix 31 clamp on it, the one that we had, what happens if we have 2 of them in series? And that's what this is. So this is just a second one of those put in series with the first one. And you can see how the line is roughly shaped the same. It's just farther down. And if anything, it even smoothed out a little bit. And that's what that's what happens with the inductance in series adds and the capacitance in series divides. So this is the quantity 2, 3 turns through a clamp-on. This is exactly this design. Okay? So this is how I came up with this design. And then if you wanted to add a third one, if you had enough clamp-on and enough coax, you could add a third one and keep going down. But again, this is better than 25 dB across the entire HF band, so shrug. Do we really need it? Are there any questions on that? That is a lot of data. And again, I was just trying to do kind of an intuitive, you can see lines moving up and down as we make different changes. Are there any questions on that?
Here's a question from the peanut gallery.
Yes, sir.
When you put those ferrites together, do you tape them together so they're right next to each other, or how do you do that?
Don't need to. And so this is that exact same coax that I was using. Oh, no, it's not. Yeah, it is. I had to cut that off. Anyway, this is the exact same coax that I used when I was taking the measurements on the table there that you can see. But I replaced those clamp-ons with some the non-clamp-on ferrites. These are just, you know, solid toroids. No, the ferrites don't need to be near each other. This is how this one is designed. I've just got 2 of them in series. Does that make sense? I don't know if you can hear me when I'm back here. Right? They don't need to be close to each other.
Okay, I got it. Thank you.
Yep. I use this as a patch cable, by the way. In my shack, I've got a patch cable where all of my antennas come in. They're type N connectors on the top of the patch panel, and then on the bottom of the patch panel are connectors that go out to all of my radios. So I can have, you know, just a little 3-foot patch cable that goes from antenna to radio. I can select whatever's on at any time, and this is one of the patch cables that I use. Okay. Then moving on.
We have a question for you, Mark.
Oh, yes, go ahead.
Yeah. If you make let's go back to the Gordon's knot or whatever, if the diameter of each turn is different, does that affect the capacitance, which would affect the resonance?
That's a good point. I have no experience, like I have never done that to be able to give you a definitive yes or no, but my understanding of how it works is that, yeah, that would help, because one of the other things you can do is spread them out this way. So like if you've got 2 loops like this, give them some space this way. That's what happens on a toroid. And I go back a whole bunch of slides to this one. So these toroids, they don't have as much capacitance as the Gordian knots that we're doing, because the coils are not immediately next to each other. That's why you don't want to put too many coils on a toroid. You want to give them some space, because the farther apart those coils are, the less mutual capacitance you have. Stuff keeps falling in my office. And that is what ends up saving you from that resonance. So yes, I think the answer to that would be yes. Any others? All right, moving on. Let's talk about some of that conventional wisdom that I mentioned at the beginning. One of the most commonly held conventional wisdom ideas for a choke is to take some coax and wrap it around a PVC pipe form or a 2-liter bottle or something like that, and just wrap it around and tape it in place, and that should be enough, right? Well, it's not great. It's better than literally nothing, but it's only about 10 dB here at the midpoint, and at best, it's not even 15 dB up at 10 meters. So, I mean, it is better than nothing. Like I said earlier, that you can, even if you've got a crummy choke, deploy it. There's no reason not to. It's not going to hurt your signal. But these measurements are just about how to improve your chokes. But even if you haven't had a chance to improve it yet, it's still worth deploying it. They may be better than nothing, but the ugly balun is kind of asymptotically approaching nothing. I couldn't hold the thing and take the picture at the same time. When I was measuring this, this coax was held tightly against the PVC. Now, maybe you could add a whole lot more turns to this. This is, I think, 7 turns. 1, 2, 3, 4, 5, 6. Yeah, this is 7 turns of coax around a PVC form. You may be able to add a whole lot more to increase this attenuation, but just wrapping 3, 5, 7 turns around a PVC form is not going to get you a whole lot. So anyone who says, that's good enough, you don't need to do any more than that, we got data that says otherwise. Having said that, that ugly may still be better than trying to do it in a Gordian knot, right? So it is better to keep it clean and, in a line like that, rather than twisting all of your knots together like the Gordian knot. So this is 7 turns on that 2-inch PVC form, and then this is the same amount of coax, only 6 turns in a Gordian knot, because the loop ended up being a little bit bigger. Yes, you have more here, but not. Yeah, it's the resonance is not good. So which one of those is better than the other, I'll let you decide. All right. Seriously, why does stuff keep falling in my shop? Anyway, questions. I promised you I would have links on the last page and descriptions of the 2 best chokes and all of that fun stuff. And so here's my last slide, but I will stand by and take any questions.
I got a question.
Can you see this?
Okay, so we're going to do the question from the room first, but I heard somebody on Zoom. I'll get back to you in a second. In the room, yes.
Okay, can you see this in the
I can.
coming from? What about this kind of a choke?
That would be a fantastic choke from the way it looks here. I bring it back out again. Is it just bifiller wound? And you got 2 conductors on each side to increase power handling?
Yeah.
Where does it go across? Because you've got them coming out both ends of the toroids. So it's not going all the way around.
The shield and pin wrap together in both directions around the toroid on opposite sides.
Yeah, there you go. Oh, I see. I see what's going on. Oh,
I found this on YouTube, and some of the YouTubes actually do the testing on it.
Okay, hold on for 1 second. So the orange is going to be sending it that way. And it's going to be sending it that way.
Orange is center pin, blue is shield.
Yeah. So, yeah, I think it looks like it would work incredibly well. I like how they split it so it goes around the 2 different sides, so it ends up on opposite sides without having to cross over in the middle.
Right.
That's a neat design. I like that.
Okay.
That should work really well. Matt's got a tester in the room. Hook it up. Let's see how it does. There you go. All right, there was somebody on Zoom. What was the question?
Yeah, this is Barry over here.
Hey, Barry.
how do you connect your rig up to the nanoVNA, and what setting do you do on the nanoVNA to take the reading and show the graft?
So you say rig? Do you the test rig? You mean? Yeah.
Yeah,
So
if we had your test rig and we
yeah.
connect that to a nanoVNA, what do we do on the nanoVNA?
So this one out. Okay. So here's my nanoVNA. I got one of the fancy metal ones, and then it's just got little 1-foot SMA cables. The back of the test rig has some SMA ports there that connect to the VNA. And so you just screw those on there. The switches there are used for the calibration process. So you flip all of the switches into certain configurations to be able to do the open, short, and load and isolation and through calibrations. You don't have to memorize all of that. It's in the documentation. There's just for this step, put them this way. For this step, do them this way.
Yeah, but nanoVNA, I know how to use it for SWR, but how would I use it to measure this common mode?
So you would select one of your traces and you put that trace into S21 and then have it measure log mag.
Log mag, okay.
Yeah, S21 log mag is what you're trying to measure. So again, that is the signal that comes out of port 1 back into port 2. So we're going through the device that we're measuring, and then we want to measure the number of dBs that signal has gone up or down coming out of port 1 into port 2. We want to measure the dB of attenuation.
Okay. And when you hook up a common mode choke to your rig, and let's say you have your transceiver going to an amplifier, going to a tuner, do you put it at the output of the tuner or the input to the tuner or between the amp and the rig?
So again, we have the two different chokes, the two different places that we want to put the choke. On the transmit side, or for protecting the transmit, you actually want it up at the antenna.
Right.
Okay, because the antenna is where the imbalance is going to be happening. I'm assuming that all of the coax and transmission lines between your radio and your amplifier and tuner, and then the tuner over the big long transmission line out to the antenna. I'm assuming all of that is nice and clean 50 ohms. That's well-made coax. We don't have to worry about asymmetries there. But when you get out to your antenna, there will be some atmospheric asymmetries, if nothing else. And so all of that asymmetry is going to create some common mode. And you want to put the choke right there between the feed line, the nice clean feed line system, and out to your ugly real world dealing with antenna, right? So this is why we put these things at the feed point of our dipoles. They're commonly called ballons, but I hate the phrase ballon because people use it to mean so many different things. The ballon that you stick at the feed point of your antenna is more accurately called a common mode current choke, and that's what we've been talking about all this time. So we want to have that choke up at the antenna. On the receive side is where you want a choke by the radio. And if you can, I assume that your receive signal is coming down your feed line through the tuner, through the amplifier, albeit through a bypassed section of the amplifier, and then straight into the rig. Is that correct?
Right. Correct.
Okay. Then you probably want to put that probably on the outside, the antenna side of the tuner, because you don't want that common mode. You want to stop that common mode noise before it hits any of your gear.
Okay.
So yeah, I would say between the transmission line out to your antenna and your outermost device, which in the situation you explained was your tuner.
Okay. And the common mode, if you have it, is going to cause noise on your signal.
It can, yeah.
Okay.
Yeah, that is one of the root causes of common mode that we want to get rid of. Yeah.
I have a question too. Mark,
Yeah.
thanks very much. Also a fellow Cal Poly Mustang alumni there. I know
The correct Cal Poly.
I agree. I agree.
The world's number 2 rated Cal Poly.
Humboldt is pretty rad.
So a lot of the chokes you show, you have wound lengths of coax around the ferrites. for certain either soda applications or something where I wanted to keep weight less and coax shorter, I wanted to look at how ferrite clamp-ons affected it. And in my ignorance, I took my nanoVNA to the input to the output and removed these one at a time, thinking that it would tell me how much it was affecting the signal. What I basically proved was exactly what you said, that these don't affect the
Insertion loss.
Insertion or the differential currents.
Yeah.
But only So I guess what I'm asking too is, have you done any testing with the clamp-ons and come to any information about? I mean, I got just these off of Amazon, so I'm not sure how I have never been able to determine if this is just on to make me feel better about it or if it actually does anything.
Well, again, Matt's got the device in the room, so you can measure it and figure out how much of that feel better is real versus magic fairy dust.
I brought a nanoVNA. I brought everything to test stuff out, and I brought a Type 31 ferrite, so we can actually play with this after the talk.
Cool. So you said you were talking about them as clamp-ons. I assume you mean a linear, where you've just got a straight section of coax and you put a bunch of clamp-ons on it. Is that what you're talking about?
That's right.
Okay.
It's like what AVR sells.
Yeah. So those can make great chokes. The biggest advantage to that style of choke is that there is no looping, so you have no mutual capacitance, and it will not resonate, or at least it doesn't resonate for a very long time, very high frequency. So that's actually the best way to make a common mode current choke for VHF and UHF. If you, even with a single turn or a single loop, 2 turns of coax, where those coax go next to each other, that can create enough capacitance to really screw up your choke at VHF and UHF. So those are pretty much the only way to go once you get into the higher frequency ranges. At HF, they still work. They are not as efficient in their use of ferrite material. Because again, they're single turn, right? They go through the ferrite once. If you made even a single loop to make it a 2 turn, that would be 4 times as much inductance for the same amount of, for the same amount of ferrite material, right? Because ferrite material costs money. If we had infinite ferrite material, we would just encase everything in ferrite material and call it good, right? So I assume ferrite is a resource that we need to hoard, basically. And so if you can put 2 or 3 turns of your coax through that ferrite material, you will get more effective use of that ferrite. You just can't go too high, or you end up with that mutual capacitance. So what it means is that's why you have to have like 3 or 5 or 7 beads on your coax. You need to have so many beads on your coax to be able to get sufficient attenuation of the common mode. Whereas I can get the same thing with 1 bead or 2 beads, but I do that by winding it through. Does that make sense?
Yeah. No. Thank you very much.
Cool. Any other questions?
Yeah, I got one more.
Yes.
So I have one of those cylinder common mode chokes that I bought from my antenna when I first got my antenna up.
Mm-hmm.
So that is basically a coax with about 7 or 8 clamps on it in the cylinder.
I'm not picturing what you're talking about.
Okay.
When you say
So
cylinder,
I have a common mode choke, and I got it from my antenna.
that's a
When
brand.
I first bought. Yeah.
Okay.
They make antennas, and they sell the cylinder type of common mode chokes.
I don't know what you mean by cylinder type.
Okay. Does anybody know what I'm talking about? Let's see.
Where you just have a straight piece of coax with beads on
No, it's a cylinder tube. It's probably about 1.5 inches in diameter and maybe about 8 inches long.
And it just has
And
the
it's got
coax wrapped around it.
And it's got a connector on each side.
Like a
And I
Palomar.
presume inside that thing, it's just a bunch of clamps.
I think they're similar to the Palomar bullets, if you know, familiar with
Yeah,
those.
they also make one.
Okay. Okay, I'm not exactly familiar with what's on the
Okay.
inside of that cylinder. So, but go ahead. What was your question?
Oh, I guess so. I guess what that is just this piece of coax with a bunch of clamps around it. That's why
Probably
when you buy it, well, that's why when you buy it, it's probably 80. You know, it costs $80. You're buying all
because there's a
that
lot of
ferrite
ferrite in there.
material,
Yeah,
right?
probably. Especially if it's a long, skinny cylinder, right? Then it's almost certainly going to be because there's not enough space in there to wind the coax back and forth.
I think that might be it. So I'll hop on the camera. Mark, thank you very, very much for
Of course.
for giving us this time.